Did you get it? Okay. I'll begin with a prayer. Dear Heavenly Father, we thank you for this day. Thank you for the visitors. I just pray you'd bless this class, Lord. Help us to glorify you in what we do this day. In your name I pray, Lord Jesus. Amen. So we were talking about how to do calculus over an abstract space. Well, we weren't really talking about that, but we should be talking about that. So that's why I'm retooling things a bit in here. So I want to talk about manifolds. And calculus. And so just the rudiments, in particular, how do you differentiate on a manifold? But before I can tell you how to differentiate on a manifold, I have to tell you a little bit about what is a manifold. So a manifold is some sort of abstract set. Say M, all right? And on this manifold, there are sets, say U, say U1, and over here is U2, something like that. and then these sets, U1 and U2, they come paired with, say, charts, which we'll call chi1, or sometimes I might just use x, chi2. I'm going to use a chi, so in case I need to use x or something else later, I'm not in trouble. But sometimes people just use like x and y for these. But anyway, these are the so-called coordinate charts. These are mappings, bijections really, one-to-one and invertible onto open sets. Let's say, I don't even really care what the name of it is. I don't know. This thing, of course, is chi1 of U, U1, and over here, chi2 of U2, of course. I'm assuming that these are open subsets of, let's say, what dimension do you guys want this manifold to be? M? All right. Good. So you're setting me on this. I had managed to make an n-dimensional manifold named M. So yeah, M, that's better. That's nice. So we want to assume that those are open sets, and they're in bijective correspondence with these subsets of M. So the pair, so chi1, oh goodness, I can't remember. Well, it doesn't matter. What I can't remember is if it's standard to put the mapping or the set first usually. These are called charts. And we assume they're compatible. And what that means is either U1 intersect U2 is the empty set, or if U1 intersect U2 is not empty, then you can look at the so-called transition function, this mapping here, right, which would be what? This would be chi2 composed with chi1 inverse, right? So if the intersection is not empty, then we assume that chi2 composed with chi1 inverse is smooth map on Rm, right? And by that I mean that the appropriate restriction, we should restrict to look at the intersection of the charts, and this will map to some kind of piece like that under chi1, and that will map over here to some other kind of piece like that under chi2, and it's going to be mapping from here to here, but that's a mapping of a function from Rn to Rn, from an open set to an open set, and so we've defined what that means to be smooth already in this course, right? We said that that's smooth. That means that it has a Jacobian matrix which is full of partial derivatives, which are continuous, and those partial derivatives you can calculate further partial derivatives at arbitrary high order. Man, this thing stinks. Phew, wowzers. Okay, so that we have to have compatible charts, and they also, they're compatible, and also that they cover if we look at, say, A, which is, you know, let's say chi I, comma ui, such that I is an element of some index set lambda, is an atlas. It's an atlas means the union over I in lambda of u sub I is equal to m, all right? And all of the charts in this atlas are compatible. So M paired with A is a manifold. So a manifold is a point set that also comes with a set of compatible charts which cover the whole set. Yeah. Yeah. Yeah, I probably need to assume both in the definition. Fair enough. Fair enough. So this is what a manifold is. Now, to be more picky, and I'm not being super picky in here, right? I mean, if you look at a serious book, they'll begin by assuming M is a second countable Hausdorff space or some such thing, which assumes certain pathologies in topological pathologies. But essentially, the topology on the manifold is built by assuming that these coordinate charts map open sets to open sets. So what's open on the manifold will be determined by what an open set down here maps up to. And that's our notion of open on a manifold. Let's talk about some examples. So here's a silly example. We could talk about, say, the z equals to 3 plane. Right? You can think of this as a manifold. And there's a global coordinate chart on this. If I say chi of, you know, x, y, z, what's the natural coordinate chart? Just get rid of z, you know, x, y. And that's going to be for any x, y, z in M, where M is equal to what? It's equal to x, comma, y, comma, 3, such that x and y are real numbers. Is this an invertible map? Well, what's chi inverse of x, y? What's that? xy3. Very good. Notice that this z had to be 3 in the initial expression as well. I just didn't write it. Example 2, how about a hemisphere? Right? We could think about a fuzzy edge. I don't want to talk about manifolds with boundary just yet. We'll get back to that eventually. I don't think that's even in McNerney, by the way, guys. Which is kind of unfortunate because we would like to talk a little bit about manifolds with boundary because we want to talk about the generalized Stokes theorem, which is concerning manifolds with boundary, which is, you know, the natural extension to calculus 3. You guys done calculus 3? Multivariate calculus, any of our visitors? Like partial differentiation? Yeah, this is not going to make any sense to you. I will not be offended if you leave at any point. You're welcome to stay as long as you want, but... Are there other... I'm the only person crazy enough to hold a class on Friday afternoon from 4:30 till 6, basically. Yeah, we go until about 6. I wasn't going to tell you guys. I just let it out. man, slipped. So if this point is, let's say, P equal to P1, P2, P3, you could define a coordinate chart. By the way, what would the atlas be for this first manifold? Yeah, it has a single global coordinate chart, right? One is enough. This one here, you know, if we take chi of P, we should let it be what? I mean, you got lots of choices. A natural choice here would just be P1, P2. I think it seemed like I'm giving you the same example again. Right? And so I should tell you what kind of sphere this is. Suppose this is, you know, x squared plus y squared plus z squared equals to 9, just for the kicks. What's chi inverse of, say, u comma v? It's u comma v comma square root of 9 minus u squared minus v squared. Right, I have a few more examples in the notes I'm going to project that are more complicated. I just wanted to write a couple out for you. So what does it mean then? Actually, let me go ahead and show you the examples in the notes, and then we'll throw in the next definition. So, come on. Come on. Where's my laser? So here's a rough picture of what I was just talking about, of course. And hopefully I've got some examples. I know I've got some examples in here which are a little bit bigger. Yep.
Just a random point of clarification. So those 2 points there, under the word compatible, 1 and 2, are those or? So they can either
Both.
overlap or not?
Oh. Well, I mean, if they don't overlap, they're compatible, you know? So, on the other hand, if they do overlap, then they have to satisfy. So this is a package deal here. Yeah. Okay, so just let's get some examples in front of us, right? The unit circle is a manifold with respect to the usual angle chart. So you could say chi is equal to theta with the understanding, what does that mean? Well, if I feed theta a point, it spits back to me the standard angle theta. So I'm abusing the symbol theta a little bit. I'm using it both as the standard angle and as the mapping, which takes in a point and spits out the standard angle. Okay, so, you know, if cosine t sine t is p and I feed, come on, I gotta fix this stupid thing. What's that? Sadness. Oh, I mean, I have a ridiculously bright one downstairs, but yeah, that one from China. I got that one from China. It's pretty nice. Hey, Daniel, would you go down to my office and get me my big laser on my desk? What? You got it? Put on your shoes first. He's a biologist or something. Let's see here. Some of the biology faculty don't wear shoes here. They argue it's better for your feet or some such thing. Yeah, I think so. Good folks. But anyway, so in lieu of a laser, I'll use a lower tech solution. So if this is the point, then when you feed the point, you get back to the standard angle. Okay? Now, the inverse to this is what? So if you feed it xy, inverse tangent of y over x will give you back that. Now that's not actually a chart on the circle, right? It's a chart on part of the circle, right? It'll give you a chart on, right, either the left or the right half of the circle, because x equal to 0 is a problem for that formula.
There's another conventionally defined arctangent function that takes two arguments and solves that problem.
Right, but still there's a discontinuity there, so it's not going to be.
What direction is it? You should go to this that way, and then down. What direction?
The stairs and down? Just stay up here, it's fine.
Go down the stairs? Yes. That's opposite.
Just stay up here, Daniel, it's fine. I found a solution, it's okay.
A stick made out of markers?
Yes, Daniel, a stick made out of markers. All right, so another example would be the plane. The plane, of course, has the usual Cartesian coordinate system. That's a global coordinate system. But you might also notice that the polar coordinate chart with the appropriate restrictions is also a coordinate system. The question then is to ask, is the polar coordinate system compatible with the Cartesian coordinate system? Right? And to answer the question, yes, it is. Because, let's see here, down here, if you calculate the transition function, as it's called, and I forget which one's x1 here. x1 is the, where was x1? The Cartesian coordinate system, right? Yeah, x1 is the Cartesian coordinate system, and x2 is the polar coordinate system. So if I take the, so if I take the inverse polar map, that gives me u cosine v, u sine v, right? U is the radius, v is the angle. And then I feed that to the Cartesian coordinate map. Well, that just spits back out u cosine v, u sine v. Yeah, no problem, guys. And so this mapping to that, is that smooth? Yeah, it's smooth. So that shows you that the Cartesian map and the polar coordinate system are compatible. These are compatible manifold charts on the plane. Well, and of course I have to restrict the polar coordinates to avoid the angle degeneracy. But there it is.
So the angle degeneracy you're talking about for example 10.1.1, does that make it not a manifold, or is
Yeah, I mean, well, no, it means that the circle is a manifold, but not with just the standard angle chart.
Okay.
You need a pair of charts to cover the circle. And that's an example we're getting to. You can also, in R3, you can define spherical coordinates, these. And yes, you can show that the spherical coordinate system is compatible with the Cartesian coordinate system, again, subject to the proper restriction of the angles to make it actually a bijection. You can, of course, also define cylindrical coordinates, and in fact, that is also compatible with the Cartesian coordinate system in R3. You can, and then the notion of coordinates we have from linear algebra. If you study linear algebra, we have an idea of coordinate systems in there, and that again is in fact a manifold chart in the natural way, because the transition functions are just linear maps which are smooth. So that's nice. So any n-dimensional vector space is naturally an n-dimensional manifold. Sometimes they're called linear manifolds for this reason. Now here's the example that you really want to see. So here's a circle, and this is a system of charts which covers the whole circle carefully. So the upper half, the lower half, the right half, the left half. So what you do is you just project right, or project down, I think it is, right? This squashes y, it says project down, project up, project to the right, project to the left. I've got pictures. Well, I have pictures eventually. Oh, yes. I'm sorry, you like to read ahead?
Well, I like to have something to read.
My apologies. Now, my larger point here is these ideas are totally compatible with what McNerney's saying, but the way I'll describe a function being differentiable and how we differentiate a manifold valued function is a little bit different. Like McNerney always goes back to Rn that's over everything, and he just captures smoothness on the manifold in terms of there existing a smooth function that encompasses the geometric set, which when you restrict to the geometric, so if there's a smooth function that when restricted to the geometric set, it agrees with your function, then that function is said to be smooth because it's the restriction of a smooth function on like the superset of Euclidean space to that geometric set. And that's pretty much everything he does. And that's fine. That's really just a special case, though, of what I'm going to say here, eventually. But I think it's important for us to get some actual examples of manifolds, so it's not just me talking about these funny pictures, you know. So if you compose the right map and the upper map inverse, so like upper map inverse, it takes x and the point over x, which is the square root of 1 minus x squared. And then the right, what does right do? Well, right sends this to that. And that's for x in the image under the right map of that, which is, that's the intersection of v plus and vr, which I really should draw a picture. This is sad. This is stupid to do without a picture. So, all right. So what's v plus? V plus is like this, right? And what's VR? It's like this. The right half. So the intersection of those is where we're studying the compatibility. That's this piece right in here. This is what I'm calling W, apparently plus R. So those points have what? These have, we have x comma y such that x and y are both greater than 0, right? In that intersection. And that's why, what? Ah, no. My markers are rebelling. That's why, first of all, the inverse map gives me back plus square root, because it's there. And then the right map does what? It takes this and it just puts it over to y. And the y here is 1 minus x squared. So then you have this mapping x goes to the square root of 1 minus x squared. Is that a smooth map? Well, it's not smooth if x equals to 1. But good news, x equals to 1 is not in here. This has x between 0 and 1 not included. So it is smooth. And the transition maps between any of these 4 charts is very similar. Almost the same kind of argument. So the circle paired with these four charts forms an atlas. And that makes the circle into what's, well, it's a one-dimensional. Oh, man. Come on. Dang nabbit. Look at that. Idiot. All right. You know, I did look at this yesterday. Anyway, so yeah, a better picture of that. And so we usually just call this manifold S1 because it's the unit circle. So it's just a one-dimensional manifold. Now, let's see here. What's this one? You can easily take that system of charts and add another dimension, right? If you let z go from over some open interval, you then get a two-dimensional manifold, which we call a cylinder. And pretty much the same system of charts will work, right? It's just a z rides along.
So we're just using 4 charts instead of 2 because it's easier.
Yeah, it's easier to not fuss with the angles, yeah. We can also take two manifolds and we can construct a new manifold by taking the Cartesian product of them. It's called a product manifold. If you have a chart on M and if you've got a chart on N, you can get a chart on M cross N by just taking the cross product, the Cartesian product of the domains, and it's easy enough to check, then that it gives you a new chart. Yeah.
So for this two-dimensional manifold, would that be equivalent, like if you drew a picture of that to like a unit cylinder?
Yeah, that's what that would be.
So it wouldn't be a sphere?
No. This would be a unit surface. Yeah, like that. Fuzzy.
Gotcha. Is this one the infinite one, the one you have there?
Oh, thank you. Yes, he's right. It's not fuzzy. It's just and I don't even know how to. Oh, man. Oh, this is infinity, and minus infinity. There you go. Whatever. There, now it's infinite. Should make my Calculus 2 students happy. They always want to put infinity everywhere. They shouldn't. So a very important Cartesian product manifold is when you take a circle and Cartesian product with another circle, you get what's called a torus. And so S1 cross S1 is the torus. If you take the Cartesian product of n circles together, you get the n torus. This is a nice, interesting manifold. You can, of course, if you're willing to pick a point and work locally, a point on the n torus is given by n angles, one angle for each circle. So if you're just working, if you're working with a donut, a nice coordinate chart is just given by like theta comma beta, where theta is the angle one way and beta is the angle the other way. You know, because if you pick any point on a torus, you can get to it from choosing the angle relative to the big circle and the angle relative to the little circle, right? Right, on the surface of the torus, right? I'm not talking about a solid torus. That'd be a manifold with boundary, which we probably should talk about later when we talk about the Stokes theorem. I'll never talk about it that technically. That'd be like a whole other course to really do it justice. But
Are you definitely taking it to the end of part 3?
yeah. That will hopefully make more sense in here when we get to it. This is the dream. It was probably in Calculus 3 a little bit much, right? It's the time of the semester you're kind of like over it, and then I'm like, hey, here, have this like super abstract, like really complicated reformulation of everything we're doing. But Thomas was happy, right? Yeah. So, how do we define a function being smooth? All right? If you have a function from one manifold to another, like this, then it's said to be smooth if what it means for a function from one manifold to another to be smooth means that every possible local coordinate representative of it is a smooth function in the sense of regular advanced calculus. So in other words, you got coordinate charts, right, from n, you got coordinate charts from n and from n, and so you can look at this corresponding function down here. Is there something wrong?
Regular advanced calculus.
Oh yeah. I said that, didn't I? Oops. I should edit the video. Let's see here. Anyway, yeah. So this would be a mapping from Rm. Oh, look, I did it right this time. To Rn. Feel better? It feels better, right? Yeah, I know. And that has to be smooth for every possible choice of coordinate chart that you can study the function in order for it to be a smooth function from one manifold to another. That's what's meant by smooth function from manifold to manifold. So,
So you mean like every point that x is in, every point that f is in?
right, if we're working from like, if M was a circle and N was another circle, then I would have to study how feeding it, how filtering through F through each one of those four charts behaved.
But you would only have to look at one or two of them, right? Because two of the charts are never going to contain any given point, or?
There's a theorem, thankfully, you're right, but it's a result, that if the function is smooth with respect to a pair of charts which covers the point in the domain. I mean, if you can find a chart which contains that point in the domain, and you can show that the coordinate representative with respect to that chart is smooth, then it follows that any other compatible chart must also give you a smooth coordinate representative. I can prove that. That's actually pretty easy to prove. Check it out. So oh, I'm going to regret that. I was trying to turn on the light. Listen, I just want us to spend some time to try to get a better concept of what a manifold is before I just dive into the formalism too deeply. I mean, I know this is formalism, but I think this for me, this formalism helps me understand what a manifold really is. Maybe it's just me, I don't know. So if I know, so suppose that this is a point P, right? And it's contained in U, right? And here's my other manifold N, here's my manifold M, here's my function F, right? Over here is f of P. It's contained in some chart over here, let's say Y. Then, so suppose that there's a chi like that. And suppose that there's also another one, a second chart, chi bar, like that. And they both are charts that contain P in their domain. They're both local parameterizations, if you, well, they're not parameter, the chart is the inverse of a parameterization, guys. The parameterization I talked to you guys about the other day, that's the inverse of the chart. The inverse of a patch is a chart. Because the patch goes the other way. It goes from the parameter space to the manifold. So I'm telling you, charts go from the manifold back down. And anyway, so suppose, like you were, Sam, that there exists, let's see, this one would be what? It would be F composed with, it would be Y composed with F composed with what? Chi inverse, right? So suppose that's smooth. Why must it be that Y composed with F composed with psi bar inverse is also smooth?
Or Y bar composed with F composed with chi inverse. If we had a Y bar.
Yeah, we could do that. I'm just
Would that follow like right?
I'm just doing this one at the moment. You want me to do both? You want me to?
If it would follow simply the same group technique.
Maybe. I think probably. So the point here is that let me try to do what you're saying with a picture. The question is, how can I know this is smooth, right? This is what? This is Y composed with F composed with chi bar inverse, right? I mean, that's what I want to, how do I rewrite this in terms of that? Right? So what do I write here? No, I mean, graphically what I just did was to go from here to here, what I did was I went up here, back down here, and then over here.
And then they have the composition of two smooth functions.
Exactly. Exactly. So this is smooth because M is a manifold. So this is a transition function. And this was given smooth by Sam. So we would not question Sam about that. And yes, you can do the same thing in the codomain. You can insert y and y bar. Yeah.
Suppose, FU is in the subset of V.
Yeah, this has to be done. This has to be done with respect to the appropriate intersection of the chart domains. Yes. Well, well, the thing is, U is open, and U bar, currently unpictured, is open. I know what you're saying. I'm getting there. Listen, these are both open sets. If P is contained in both of them, there is an open neighborhood around P, which is also contained in both of them. So we can study differentiability about P, because there's an open set which is around P, common to both, where all of these maps make sense, suitably restricted.
No, I'm talking about F.
About what?
F, the function F. Like, you map F, P to F, P, yeah, I understand that, but what about the open neighborhood around P? What maps to it?
Because F is defined on M, right? So,
Yeah, I'm looking at F being defined on all of M.
so that,
Yeah, I mean, like, what FU maps to?
Well, I mean, I suppose it might just map to, I mean, it could be a constant map. It might just map to f of p. That might be the only thing that the whole M maps to. I don't know. N is the codomain.
and then we can make all these composition of smooth arguments just because we already have mapping to concrete coordinates for everything.
Right. So the larger theorem that I'm sketching, admittedly sketching, is that if you can check smoothness with respect to a pair of coordinate charts which covers the whole domain and the whole image, but I think if you've covered the whole domain, you've covered the whole image, right? I mean, so if you do that, then all other compatible charts are automatically giving you smooth representatives because of this little calculation. So for example, if you can show a mapping from R2 to R3 is smooth with respect to the Cartesian coordinate systems, it then follows that any local coordinate representative of that with respect to polar coordinates, or pick your favorite cylindrical coordinates or whatever, those local coordinate representatives of F are also going to be smooth by this observation. Now the other thing we should talk about is if you've just got M and you've got a function that just goes to the reals. What does it mean for that to be smooth? What do we mean by a smooth function? So suppose at a point P, what does it mean for F to be an element of C infinity P? What that would mean is that that's a function which is from the manifold, is a real valued function from the manifold, which is defined on at least some open neighborhood of P, right? It's smooth. And what we mean by that smoothness is that its local coordinate representative is, right? So we pick our U, and so this is our chi, it goes down here to our Rn, and then what's this? Yeah. What do you say, F composed with chi? I can't do maps. Is it chi inverse? Yeah. Do I believe it?
No, that's right.
I think I believe it. Now, if you want to get picky, you can expand this picture further. You can go, it's the reals, and over here I have the identity map, right? And so here's the identity map to the identity map on R is this coordinate chart. And so down here you have chi inverse composed with F, composed with the identity. But this is dumb, so we just want chi inverse composed with F, which is going to be a mapping from Rn to R. We want this to be smooth. Gosh. So it was id. I told you this is it's a challenge. I mean, even though I draw the pictures, it doesn't always, I don't always think through the pictures, and if I don't think through the pictures, we're in trouble. So this is what it means for a function on a manifold to be smooth. It means that its local coordinate representatives are smooth. So how do we differentiate a function on a manifold? So let's suppose that we have M a manifold and P an element of U, which is the domain of a map chi, and chi is actually X. It's x1, x2, xn, because we're M, right? So this is the coordinate chart. So it's going from U to Rm, right? So x sub j is a mapping from U to R for j equals to 1 to m. So given this, we can define partial derivatives if f is an element of C infinity p, then we say partial f, partial xj at p. What's that going to be defined to be? How do you define the partial derivative of a function on a manifold? You differentiate with respect to the jth Cartesian coordinate the local coordinate representative of it. Let's see here. So I need to draw a picture. This helps me keep track of what I'm doing. So this is what was this? This was I have trouble today. I have trouble every day. F composed with chi inverse, right, or x inverse.
What's the difference between our xj and ej here?
So down here, this is u1, u2, um. So I'm using u1 through um for the Cartesian coordinates in that Rm.
So are we assuming that M is defined as a subset of R something? Because like if M is more abstract, then what are our x coordinates, like, other than just the coordinates under time?
I'll try to give an example, but let me give this. So this would have to be F composed with chi inverse, right, of well, chi of p, but that would be u1, u2, um. All of that evaluated at chi of p. So what I'm saying is you differentiate the local coordinate representative with respect to the Cartesian variables, right, downstairs. And then you plug in chi p after that's done. Let me,
So
yeah.
xj is just like one of Kai's.
Right. Oh man. Well, I almost got it. Let's see. I'm trying to think if I could think of a good, yeah.
When you said the definition, you said M and P is an element of U, which is the numeric I, and I is X1, comma, Xi, comma, dot, 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 Xm. Did you mean to say that that's Xj to follow with the rest of the?
Yeah, that's xj because I'm trying to say that each one of these has U as its domain, but its output is just one of these over here.
Yeah, so would that be Xj up in there? Instead of
No,
X-
no, j is not a variable. J is ranging from 1 to m.
I think he just means when you say Kai equals x1, xi, and xn, like should that be just like x1, x2 to xn, or like is the I there for?
No, it's the two.
Oh, it is.
Two.
Oh, I thought that was a dot.
Oh, it looks like an I.
Is that?
It's two.
Oh, that's from last. That's from the last lecture. This is why I should clean the board more carefully. So sorry.
Okay, that makes sense. And we're good.
Okay. Here we go. Curses. I was going to foolishly try to give you guys an example. Come on. Well, you let me. It's like you turned it off that you get to keep it off for a while. Let's see here. How about I'm trying to think here. I'm sorry. Everything I can think of is like going to eat a stupid amount of time at the moment, and there must be a simple example I could give you. You know what? Let's just. It may already be in here even.
How many of this what picture do you have?
Hmm?
How many of that picture do you have?
So there's that one. Oh, yeah, I kind of buried the lead. One of the interesting things you might say, if you have a function f like this, and it's smooth, if you have a smooth map from m to n, and it's also a bijection, and it has a smooth inverse, then f is what's called a diffeomorphism. And then these two manifolds essentially have the same manifold structure. They have the same.
Like circles to ellipses, for instance.
Yeah, circles to ellipses. Sure, yeah. But it's, that's, I think, one of the, that is essentially the problem of differential geometry at large, is to classify when different spaces are diffeomorphic. So that's a hard problem, but you could study the mappings from one set to another, and that's part of, that is by definition what it's about, but.
Is that what people say when they talk about like topological equivalence, like the torus?
Yeah, related to, I think diffeomorphism would imply homeomorphism would be topologically equivalent. So a diffeomorphism would automatically be a homeomorphism. It's got more structure. There's this whole differentiable manifold thing you're floating around. It's possible to have spaces which are homeomorphic but are not diffeomorphic.
Like if it's got like, I don't know, hard edges. I'm not totally familiar.
Yeah, I'll leave it for another course, but these are not equivalent ideas. They're related, but they're I think diffeomorphism is stronger. The interplay between these two ideas is an ongoing problem of mathematics. Annoyingly, these notes do not quite join up to where I am logically at the moment. So my notes, and I'll just follow them, and we'll get back to here eventually. Sorry about that. Think of it as a DC movie. All right, it's just either a plot hole or a time skip, however you want to look at it. Come on. This is, all right. So I introduced, so smooth functions at a point. We could talk about derivations. I introduced these last time, right? Derivations are linear and they obey the Leibniz rule. They act on smooth functions, give back smooth functions. And I give examples here. So if you need to go somewhere, what is it? Are you he's just plotting, all right. So obvious derivations would be the manifold of the real line and just ordinary differentiation operator. That is a, oh, thank you. That is a derivation on smooth functions defined near T naught, right? If we look at the plane as a manifold, right? The partial derivative with respect to x or y, these also give derivations. Great. Of course, if you're in Rn, I mean, okay, great. I have some really, really complicated examples here. So yes, partial derivatives are derivations. I would add one to this, and so this is part of the reason I wanted to do this with you guys. There's another manifold. How about this? R n by n, right? This would be a manifold, and the global I mean, any vector space is. We can use the global coordinate system. You know, we could say xij, right? That takes in a point A, and what's it give you back? Just the components, right? It's not hard to prove that this is in fact a bijection, right? And so you could calculate things like partial xij with respect to that definition. If you had a function, let's see here, all I can think of at the moment is determinant, and that's really not helpful. How about the trace? Okay, Daniel, thanks. Okay. But my larger point is that this would give you a derivation on smooth functions from smooth functions that take in a matrix and output a number. I'm trying to think of what would be a good example of a. Oh, how about this? What if we define f of a equal to, let's say, a12 plus a34 squared? You could do that. I mean, that would be a real valued function of matrices. And then, so this is kind of, this doesn't help you understand the definition much, though, unfortunately. See, because when I calculate partial xij of f, you know, at the point A, let's say, you know, then I'm telling you over here, it's, you know, I don't know, like I'll tell you how it works out. Stink. So let's see here. I'm sorry, I really should write this in terms of x. So this, and to be more clear, I should really write it like this. This is a helpful notation because it just saves you a lot of writing. So what I'm saying is that f is the function defined to be the 1,2 coordinate map added with the 3,4 coordinate map squared. When you work through the details, like partial f partial x 3, 4 at A is going to be, not surprisingly, 2 times A 3, 4. This is not a,
The squared can just be in composition, right?
no, I mean, I'm talking about F. This is literally the, I mean, if I feed this a matrix, F of A is x1, 2 of A plus x3, 4 of A squared. It's the pointwise multiplication of real valued functions. Yeah, good question. So that is A1, 2 plus A3, 4 squared. I'm sorry, I promise I'll find you guys a really abstract example to illustrate this differentiation thing next time, okay? I just don't have it on hand, apparently. So this is the definition I just covered up partly. So the inverse of the patch is the chart, right? And so to differentiate a function on the manifold with respect to the jth coordinate of the manifold, we differentiate the coordinate representative of it with respect to the jth Cartesian coordinate. And see, I've written it in terms of the patch here. And here, this is in terms of the patch. This is in terms of the chart. Whichever makes more sense to you, you can in principle think of. But manifold theory tends to live over here. Elementary differential geometry tends to live over here. I mean, you can either write everything in terms of patches, or you can write everything in terms of charts, or you can try to do both. I think a healthy mixture of the two is not a bad thing. But anyway, so this is the local coordinate representative of F, and that's how we partial differentiate. Anyway, so let me get to the point. Sorry, I don't have a good example for you. It's all my fault. But the beautiful thing is, well, here's a picture of what's going on. You know, I mean, what we mean by partial F, partial xj, it's really the time derivative of F composed with that particular line, right? And that is exactly, of course, a directional derivative. It's a directional derivative in some, I mean, we're taking a line down in the, you know, the parameter space of the manifold, and this is getting mapped up to some grid up here, and we're studying how F changes along these curvy lines that are the image of that, and that's what partial F, partial xj is telling us about. That helps. So here's the properties of partial derivatives on manifolds. Derivative of the sum of the derivatives. You pull constants out. You got a product rule. You have independence of coordinates on the manifold, just like you have independence of Cartesian coordinates. If you have two different coordinate systems, x and y, here's how they're related, like partial x, partial y at p times partial y, partial x at k. Notice that the k is summed over, but the I and j are free. That gives you Kronecker delta ij. Finally, if I want to relate the partial derivative of a function on the manifold with respect to one coordinate system to the partial derivative of that function on the manifold with respect to another coordinate system, they're related in this way. This is the chain rule. Yeah.
What if the functions are divided by each other? Like a quotient rule style?
A quotient rule. Yeah, I think we can. I think we can derive the quotient rule like we usually do. Yeah.
Wait, do we have a power rule here? Because if we had that.
Yeah. Well, power rule is going to follow from if we take like here xi for the function. Like think about the case that the function is the coordinate, right? Like xi times xi would be xi squared. This would give you xi partial xi plus partial xi, they give you 2xi. So like we get the power rule for integer powers from the